the coffee cup calorimeter examples. We'll start with this one, in which we are mixing sodium hydroxide and hydrochloric acid. Got our calculator with us. Looks like we have, we need to know the reaction. The reaction is a very familiar reaction. If this were an exam, the reaction would be given. It's going to be hydrochloric acid plus sodium hydroxide forms, reacts to produce water, and sodium chloride. Now, so these, we have volume of molarity sodium hydroxide, same information for hydrochloric acid. We mix them together in a coffee cup calorimeter, and we find the temperature of the solution increases from 23.4 to 30.4 degrees. Determine the heat of reaction. So there's definitely a reaction, and if I give you a balanced reaction as part of a problem, then there will be a reaction, and you'll need the reaction coffee cup calorimeter equations. So system is reaction. Q reaction equals minus Q solution. Okay. And the way this works is, since we're finding delta H reaction, we're going to work on the Q reaction part second. We'll solve Q solution first. We've got mass of solution, and the specific heat capacity of solution are going to be the same as if it was for water. So we can say the mass of the solution for a total of 500 milliliters means that we're going to have 500.0 grams. Assuming the density of the solution is the same as that of water, which is a good approximation. Specific heat capacity of the solution, same as that of water. That is a good assumption. And important here, T final is the 30.4 degrees. T initial is 23.4. And we have all the information to find Q solution. And let's multiply this out. Let's do the temperature change first. 7 degrees times 4.184 times 500. We get 14,644. And we can see our grams cancel and our degrees Celsius cancel. So that's joules. And Q's are heats. They will always have units of joules. We can tell them apart from our delta H values, because our delta H values will always have units of joules per mole or kilojoules per mole, depending upon the problem. All right. Now, that is a positive amount of energy. That means that the solution is giving off energy, is taking in energy. The reaction is giving off energy. So Q reaction is minus 14,644 joules. Q reaction equals delta H reaction times moles reacted. We still have to find our moles, but we have our Q reaction. We're looking for our delta H reaction. So let's find our moles now. You can see that we have the same volume and molarity of each of these. So this is a problem where each of our reactants is limiting, and So if we find the moles of one, it'll be the moles of the other, and it will be the limiting reactant. I'm going to solve that over here. So we have convert our milliliters to liters, convert our molarity, either one, let's just use sodium hydroxide for this example. 1.00 molarity sodium hydroxide is 1.00 moles sodium hydroxide per liter of solution. Our liters cancel out. Our number 0.250 moles, and those will be our moles reacted, whether they're sodium hydroxide or HCl for this problem. We'll do later problems in which there is a limiting reactant, and we have to solve for that as well. So minus 14,644 joules, that's our Q. We don't know our delta H reaction, and we do know our moles. And then our delta H reaction, 14,644, well, with a minus sign, let's see, good, divided by 0.250, we get minus 58,576 joules per mole. Rounding that to 3 sig figs, like we always do for our final answers. 5.86 times 10 to the 4th joules per mole, and that is our final answer for this. Now, sorry, one other thing to say. So this delta H is negative because the reaction is exothermic. An exothermic reaction heats up the solution, so positive temperature change for the solution means negative value for delta H reaction. This is another example, and this one that says the dissolving of ammonium nitrate is used in chemical cold packs if a certain number of grams is dissolved, and this time we have been given the dissolving reaction. Delta H dissolving. So this is a delta H reaction for a specific type of reaction. So we've used the subscript dissolving, but we could have very easily just using delta H reaction there. Functionally, it's the same thing. It's like dissolving is a specific example of a type of reaction. In either case. All right, so now this time there is a reaction. I'll write it up here. Minus Q reaction equals minus Q solution. What is the final temperature? The final temperature is going to be part of the Q solution term, so we'll solve for that part second. Let's find our Q reaction first. That's going to be delta H reaction times moles reacted. To find our moles reacted, we're going to go ahead and take our grams of ammonium nitrate that are dissolved, turn them into from grams to moles. Our delta H reaction is given. We'll find Q reaction. Do notice that delta H reaction is given in kilojoules per mole. I don't know about you, but I'm a joule person, meaning I work all my problems in joules. I will convert that to 25,700 joules per mole. I move the decimal point 3 places to the right to turn kilojoules into joules. To get my moles, you get the molar mass of ammonium nitrate. I think I've got that over here somewhere. Yes, 80.05 grams of ammonium nitrate. Oh. when I multiply this out, I get 0.338 moles. There's only one reactant, so it must be the limiting reactant. I get, well, 8686.6 joules, just joules. That is a Q value. I know that my Q value for reaction, add a minus sign, I get Q. Solution. See, as long as there's a minus sign in here, as long as it changes sign going from reaction to solution, either version of this is fine. And again, I'm just going to keep all my sig figs for now. Always round my final answer to 3 sig figs. Now, Q solution is going to equal mass of solution, specific heat of solution, times, and this time, T final minus T initial of my solution. Let's plug everything in we know. I know my Q solution, it's negative. I know my mass of solution, well, all right. We know our mass of ammonium nitrate. It is mixed with our mass of water. 100 milliliters of water is 100 grams. So my total mass of solution is actually 127.07. My specific heat, same as water. T final, I'm just going to write TF because there's only one TF and we don't know it. TI, 25 degrees Celsius. Now, there's only one equation, one unknown. We're off to the algebra races. Let's see, I'm going to multiply my right-hand side out. So it's going to be equal 531.7, still keeping more sig figs than we need, times TF minus this times 25, 13,292 equals minus 8686.6. Getting rid of my units there for a second. Don't like that, but I'm going to do it. And then add this to the other side. I get 13,292 minus 8686.8. I get 4605 equals 531.7 TF. Divide through both sides by 531.7, and I get 8.66 degrees Celsius. It's of my final temperature. Ooh, sorry, I cut out there for a second there. And that is a good temperature. It is lower than the initial temperature because endothermic reactions with positive delta H values lead to final temperatures that are lower because the reaction of dissolving takes in energy. That is how we know ballpark temperatures should be lower than we started with. All right, that's 2 examples. We'll do one more example in this video. This is going to be, so that's 2 with a reaction. Let's do 1 with a material. The material one goes like this. It is a piece of aluminum. It has an initial temperature It is submerged into some water at a specific temperature. What is the final temperature of both substances at thermal equilibrium? Thermal equilibrium, just thermal means temperature. Equilibrium will mean everything seems to have stopped or has stopped changing. Another way of saying that the final temperatures are equal to each other. This is a material, and that material will give up energy in this case, since it's the warmer material, to water. Minus sign shows the difference in direction. Now I'm going to plug everything in. I'm just going to plug everything in directly from our equations. It's going to be mass times specific heat times temperature change of our aluminum. My mass of aluminum, my specific heat is given for my aluminum. My T final for my aluminum is not known, but my T initial is 45.8. Do not forget the minus sign. We included it. All right, so mass of water, specific heat of water, and temperature change of water. T final water minus 15.4. Ooh, and it just makes it. Now my T finals are the same, so now it's off to the Algebra Olympics. I'm going to multiply the left-hand side out times, good, 0.903 equals, so I get 29.34 TF, because the multiplying these part out, times a minus 45.8. I get 1344. Multiplying out here, minus times 4.84. I get minus, let's just get rid of that, minus 441 TF. I get a minus and a minus. Two minuses make a plus. Then I multiply that times 15.4. I get 6785. Now I have two TF terms. I'm going to collect them on the left-hand side so that this becomes positive. So 29.34 plus 441. I get 470. Then this on the other side, 6785 plus 1344. Divide through. And I get my final temperature, 17.3 degrees Celsius. There's 3 examples. There's another example on the next page. That is going to be a companion problem.